Hello, hello, hello. It's Will. Welcome back to From Bronze to GM and miniKanren, episode 13. Today is Thursday, March 6th, 2025. I actually tried to record this video last night. Got about an hour in, and I had made a bunch of mistakes, so I trashed it. It's like, let me try tomorrow. They weren't like Bob Ross happy accident type mistakes. They were just things like, oh, I accidentally showed all my emails. About the third time I did something like that, I was like, oh, I can't really edit it out at this point. So it gave me a chance to rethink things. So I ended up with a different sort of episode. So hopefully it works out better. But yeah, that happens, right? That happens. Well, last Sunday I had an Out of Touch Sunday. Remember the Hall & Oates song, Out of Touch? And there's this internet meme, Out of Touch Thursday. Well, today is Thursday. And for me, Out of Touch Thursday or Monday or whatever day it is means I can be out of touch with the news to a greater extent. And so yesterday, I think I brought in way too much news the last couple of days. And today I was like, I'm just not going to do it. I'm not going to check the news. It's hard to avoid it entirely. And so I did see a couple of things, but yeah, so this has greatly improved my mood today. And just speaking as a private citizen, not having anything, not at all related to, my employer or anything like that. Speaking as a private citizen, I am very concerned about things going on in the world and things going on in the United States and things having to do with science funding and, the research infrastructure of the United States, all those things. Very concerned to see that universities are starting to turn away PhD students and medical students who they had offered admission to their programs. All sorts of things going on right now. So that is deeply concerning to me. At the same time, I remind myself of what was going on in the UK in 1939 in preparation for World War II. They had these posters, "Keep calm and carry on," and I had thought that actually these were never shown in public. These were for reserve or something, but apparently they were shown. So here's one that apparently is original. So some of those were displayed, and it's not just the famous keep calm and carry on. Oh, that's the most famous of them. There are apparently two other varieties. Freedom is in peril. Defend it with all your might. And then there's another one, which I especially like, which is your courage, your cheerfulness, your resolution will bring us victory. Courage, cheerfulness, and resolution. And I would add to that kindness, being kind to each other. So I I look at these every day, and in particular this one, okay? Courage, cheerfulness, resolution. And I was watching, as always, I can try to make a StarCraft analogy. I was watching Vibe's, let's see, I guess his final Silver 3 into Gold 1 games, I think it was. It's either that or the beginning of Gold 3. Sorry. It had been Silver 1 into Gold 3. I think it was like one of the last games, or it was one of the first games of Gold 3. But he was playing Zerg, and his natural got cannon rushed. So, actually first the Protoss probe comes in, double gas steals in his main. And he's like, what are we going to do? Are we going to, pull all our drones? No, we're not. We're going to keep calm. And then he checks with his overlord, and he sees that there's a pylon being dropped. And so he pulls some drones that are mining in his natural, and then he sees that there are already cannons that have finished. He's like, okay, the cannons have finished. What are we going to do? We're going to keep calm. So he takes his queen from his natural, moves it up away from the cannon so it won't get aggroed. He brings his queen down from the main after he's injected. He keeps up with his injects, and he makes a few lings, and then he also immediately throws down 3 spine crawlers in his main out of range of the cannons, and then he says, okay, once the spine crawlers are done, here's what we're gonna do. He uproots the spine crawlers, moves them down right next to the cannons, and then implants them, and then while he's doing that, he comes in with the lings and the queens and takes care of it, no problem. I've lost that sort of situation so many times. And one of the great things is, as soon as he's doing that, he goes back just to making drones. Like, right? I mean, he hasn't taken out any of the cannons or any of the probes, but he's immediately just making drones. It's like, okay, we're short a bunch of drones now. Start droning again. Okay. And then immediately go back to the inject. So just go back to this macro, the macro cycle. And he just doesn't get flustered. Right. So that was like his version of keep calm and carry on. And that, I think, is a lesson also in that, when you get cannon rushed or you're getting cheesed in ladder on a tournament game or whatever, part of what the opponent's trying to do is fluster you. Part of what your opponent's trying to do is get you to despair or lose your sense of courage or sense of humor, or to give up and, or make an unforced error, right? And just like, you yourself give up just because your plan is not, has been thrown off. And watching Vibe handle that was great. It's like, okay. And then, the fact that or he'll be, I've seen him where he's, he loses one of his bases and he's in the middle of fighting an army. And in the middle of the fight, he's like throwing down the base again. He's like rebuilding the hatchery in the middle of the fight. It's like, okay, I think we were going to win this one. We're not going to wait. We're just going to go ahead and start rebuilding. And then he'll start making drones again in the middle of the fight because he thinks he already has enough. And if he doesn't, then he'll have to pull some drones and, from a mineral line or make some more units. But he's the epitome of keep calm and carry on. And he doesn't lose his courage or his cheerfulness or his resolution. So I appreciate that. Yeah. So I'm going to try to keep that in mind and in my heart. So I wanted to revisit some remarks I had made in a previous video about researchers who go after low-hanging fruit and who don't necessarily have a vision. I just had some more thoughts about that because I'm always worried when I say things like that people won't understand what I actually think. Maybe I'm just not communicating it clearly, so I'll try again. And one reason I wanted to mention this is that I saw Dan Liu post about this. It's called What to Learn. And I'll have a link in this document or whatever. But in any case, the idea in this post is that many successful researchers and mathematicians and physicists, they really only have a few tricks, and people have been critical that someone made a whole career out of using the same tricks over and over again. And here is talking about Paul Erdős, one of the most prolific mathematicians in a long time. In history, very interesting mathematician. There's a book about him called, I think it's called My Mind is Open, that I found interesting. And apparently he was criticized for just using the same techniques over and over again. And even Hilbert apparently tended to use the same things over again. So the question is, should you learn everything, to some extent, or should just like learn a few techniques and just apply it? And certainly Erdős made a huge contribution to mathematics, just in terms of like, going after a zillion problems. So, that works. And Richard Feynman apparently had this saying, which I've read in text. I've never seen a video where he talks about it or anything, but he said, it's like how to appear like a genius. You keep 20 techniques. You have 20 techniques that you know really well, and you have 20 open problems, and you know both of them well. And every time you say you see a talk or read a paper or have a conversation with someone, and they show you a new technique, then you match that technique to your 20 problems. Okay. Can I get unstuck on any of my 20 problems or make progress on any of my 20 problems with that technique? And similarly, if you see a problem that someone presents, you say, well, I've got these 20 techniques, and, some of them at least are going to be, usually there are 20 techniques that maybe aren't standard, or these are uncommon problems, uncommon techniques. And whenever you see a new problem, you think, okay, do any of my 20 techniques, could those be applied? What would happen if I applied, which of the 20 techniques seems most applicable here? And, how can I apply it? So, that's how he says you can appear like a genius. And certainly with, things like miniKanren relational programming, I feel like I definitely feel that, because in relational programming, you run into a bunch of problems that you just don't see, even in standard logic programming, let's say, or non-Turing complete constraint programming, those sorts of things. So I certainly have a big bag of open problems. And also there are a bunch of techniques I know, for example, having to do with relational interpreters, that I think are very unusual techniques. And, so I practiced that long before I heard the Feynman version of it, but that makes sense to me. And also, day 9 has talked about the difference between a good StarCraft player and a great StarCraft player. And he said, if someone knows, 20 builds and can execute them really well, they're a good player. If they know one build and they can execute it perfectly, they're a great player. Right. And, an example of that would have been Stefano's Roach build that was so overpowered that, like roaches got nerfed in StarCraft 2 after he was so dominant with it. That was an example of, he was just a great player. He could beat any of the Koreans using this technique where he didn't play reactively. And in fact, his opponents knew exactly what he was going to do. He was just going to do mass roach. But he could execute it so well, even though everyone knew he was going to go mass roach, like they weren't able to stop it. So it's not like, I think that having a small number of techniques, or having a small number of problems you really care about, isn't important or useful. And, by all means, if there's low-hanging fruit, if you see a problem that's open for which one of your special techniques seems super applicable, yeah, go for it. Sure. I guess what I mean is that, okay, I'll make another analogy. This is to the X-Files, right? One of my favorite TV shows. And X-Files has like sort of two types of episodes. One is the monster of the week. All right, hey, people in New Jersey have seen this thing as kind of like a Bigfoot. Okay, let's go investigate that. And then there's another type of episode, which is like an arc, which is often called grand conspiracy and has to do with extraterrestrials and all this stuff, right? And so that goes throughout the whole series, and through at least one of the movies. And now, I actually, of the two types, I actually prefer the Monster of the Week, because there's some really incredible Monster of the Week episodes, especially in season 5, like Bad Blood, for example, Monster of the Week. So I think it's sort of like in the middle of the series, they really hit a stride. And one of the Monster of the Week episodes, I think it was also in season 5, had Bryan Cranston, and, it was like all of the Monster of the Week stuff led to the spinoff show The Lone Gunman, and eventually to Breaking Bad and Better Call Saul. Some of the best TV series ever. And so actually, this is close to my heart, the Monster of the Week. At the same time, like, I guess having a vision is more like the grand conspiracy thing, right? Where it's like, this is something that you pursue over a long period of time. It's not like, okay, here's some low-hanging fruit, I applied my technique. Here's some more low-hanging fruit. It has nothing to do with the other. I applied my technique. No problem with that. Go for it. My personality is such that I also want to do things that add up in a way that's nonlinear over a long period of time based on a vision that I have. Okay. So, low-hanging fruit could be in pursuit of a vision. Maybe it's a vision about making programming more secure, or making programming easier, or whatever. I think having a vision is somewhat different. It's like, hey, here's a particular way I see programming could be done, or whatever area of research it is. And I don't know how to get there yet, but I have some ideas, and I'm going to try to keep directionally towards that. And sure, there might be lots of low-hanging fruit along the way. However, I am going to judge, say, what I work on, not just on, can I get a publication out, or can I do a cool demo, but, does this move me closer to the vision, or help me understand the vision more, or help explain the vision to other people? Okay, so that's what I mean. Okay, so I think hopefully that explains it. Okay, enough of that. Okay, some more stuff about quasiquote. Got some nice comments, emails, comments on videos, and also comments in Discord. And speaking of Discord, by the way, Discord is yet another platform owned by a big company or whatever, right? As is YouTube. I don't know, maybe it's good to go Fediverse or something. Like, at one point I was uploading videos to archive.org, but I don't know, that's really the purpose of archive, to just like upload these videos. Maybe, I don't know. But also archive's got some legal issues, so I'm not, I don't know what to do, but kind of having all the Discord stuff, having that conversation in Discord, I don't know, maybe there's some other way to do it. I'm growing increasingly skeptical of having all of our infrastructure controlled by giant companies and billionaires. Speaking as a private citizen. Anyway, but thank you for the comments, the various sorts. That helps a lot. One comment I got was a link to community.schemewiki.org. I guess that page is offline now, as this is the Wayback Machine. Looks like the page was 2006 to 2024. I don't know if that's still up. Let me just try that. Can I open it? Oops. No, not DuckDuckGo. Come on. Yeah. Well, maybe it's not up. Anyway, this is like a FAQ, or frequently asked questions, and it has to do with R5RS scheme, it seems like. And one question is, can quasi-quotation be implemented as a macro? So Scheme has a very powerful feature called macros that allow the syntax of the language to be extended or changed. And we'll definitely get into macros. Very powerful. This is one reason that people use Scheme, and definitely a big reason people use Racket. And it's also a major area of research in those languages. But can quasi-quotation, which is a type of syntax, and then to go with it, unquote and unquote splicing, can that be implemented as a macro? There are different types of macros in the history of Scheme. One system that started, being official as when R5RS came out is called syntax rules. So you have defined syntax. We're going to define new syntax called quasiquote, and we have syntax rules, and then we have this list, optionally empty after syntax rules, which is a list of the auxiliary keywords. So like you can only use unquote and unquote splicing within quasiquote. So these are the keywords that have to go with the macro itself. Okay, so you have to use those within the quasiquote. And we'll see that there are other things like else. Else is an auxiliary keyword within the cond macro, for example. So there are a number of these in Scheme. But anyway, here is a purported definition of quasiquote as a syntax rules macro. And this also supports the vector stuff with like vectors like arrays in Scheme. So, and it says the expansion is not optimal. It does not exploit Scheme's ability to represent constant lists and vectors as literals. It is possible to write a macro that does that, but it's rather long and hence not included here. So this is sort of the simple version, but not the industrial strength version that would be as efficient as you want. So I was interested to see this. Thank you for pointing this out. I've got a link to this in the document, the epi13.txt. I'm going to start including and cleaning up the links to these documents instead of just pasting the text into the comments for YouTube. I also have a GitHub repo that has all these files. And once we start getting into writing more code, that repo will become increasingly important. The other thought I have is, okay, so this is apparently not a very optimized version, right? Or optimized at all, I guess. I happen to know that there were some issues with the R5RS report, and there are things like handling of rec. There's some issues. So I don't know if, when I look at something like this, I don't know if this is I don't know how to assess this particular version of quasiquote. This looks like the sort of thing maybe I'd want a fuzz test where I would try, generating random expressions using quasiquote and unquote splicing, and comparing the behavior from, different Scheme implementations that claim to be R5, and with this implementation to see if they produce the same results. And also remember in R5RS, we found that interesting wording that apparently goes back to R3RS about the behavior of quasiquote being unpredictable if unquote splicing or quasiquote were to appear in sort of the wrong positions internally. Which that wording appeared to go away in R6 and also R7 small, although I'm not sure exactly why that went away. So anyway, not sure exactly how to assess this particular implementation. One thing we could do is look at the implementation of quasiquote, both in the Alan Baldwin paper in the appendix to see if that matches this, or also look at the implementation in Shea Scheme or Racket or one of the other systems. We just have to be a little careful because I think this is supposed to be like an R5 version as opposed to R6. Part of the issue of looking at something like the Shea Scheme version is the Shea Scheme version is definitely going to be optimized, like almost certainly going to be optimized. And it may not be implemented like this at all. It may be part of the macro expander, which is quite complicated, and the same with Racket. So it may not be easy to tell how close this is. These are advanced things, okay? I was watching an interview with Vibe today where someone was asking him about teaching StarCraft and his philosophy. And, he's changed between his 2019 Beta GM series and his 2021 Beta GM series in terms of what he thinks is too advanced for people at different levels. And like he talks about micro, he's like, until you get to Diamond, you shouldn't be doing any micro at all, really. Like, maybe you'll box select some drones and click A to attack some cannons that are warping in or something like that. But that's about it. Like, you really shouldn't be doing micro. You should, because you can't micro and macro at the same time, and it's the macro that's more important. And of course, I think about this as well in terms of what I show you. So here we go. We're still dealing with pairs and, tree structures. And then here's a definition of a macro, and we're getting into like the differences between the R5RS report and R6RS and things like that. But this gets back into the idea of what do I consider important for someone who really wants to go far and understand programming languages, programming language research, ideas of programming language design, comparisons of different languages and different versions of languages, all those sorts of things, abstractions, designing abstractions, reading papers, implementing papers, writing papers, maybe, all those sorts of things. And so, yes, we're not at the point now where we're ready to talk about macros, but even though we're still doing these elementary things, having to do with cons pairs, right? Like everything we're doing so far is like about cons pairs in some form, and symbols and con pairs, atoms and cons pairs. It's still not too early to know that there are these things called macros, because that I think is part of the sort of tragedy of how scheme is usually taught, say, to undergraduates, is that because a subset of scheme can be a very nice, concise notation for computation and talking about computation, it's quite possible to take a course on using scheme and never see any of the really powerful features, which are why, like really good computer scientists and programmers actually like the language, right? Like, people who've been programming in scheme for, 25 years or 50 years at this point, they're not still programming in it because they're beginners, right? They're still programming in it because there's something about the flexibility and the ability to create abstractions, and there's something fundamental, and there's something really nice and composable about the design. And the macros are a big part of it. And the fact that you have these macros and the S expression, notation in scheme, and also things like quasiquote and pattern matching, all these things go together in a very beautiful way that we'll see. So I want to just give you pointers to these things. And also at the same time, I want you to be exposed to the wider world of ideas. Like, know that there are these macros. Know that, it's at least possible to create a quasiquote macro. And also something I'll tell you is that if you're building a pattern matcher in scheme, it's not uncommon to redefine quasiquote. Okay, so people redefine these things. That's one thing that's very powerful in scheme is you can take something that exists in scheme like lambda or cond or if or quasiquote or define, and you can change them. You can change how they work syntactically, or bind them to a different procedure. If you want plus, the variable plus, to actually do multiplication, it's like, well, that's your business. It may be a little weird, but you can do it. And if you want quasiquote to have a totally different behavior, you can do it. Sometimes there are reasons to do it. There are reasons to change the behavior of quasiquote, especially in pattern matching. There are reasons to change the behavior of lambda. those sorts of things. So, and also when you're doing like domain specific language design, like you want to make a little logic language like miniKanren, it's very handy to be able to add new syntax. And also by using things like libraries or modules and controlling namespaces, you can say, you know what, we're going to not give the user most of Scheme. We're only going to give them what they need to do the little language, and that can enforce, say, like syntactic restrictions and also restrictions on what sort of operations are available to make sure that the language is sandbox and is safe, things like that. Like you can't delete a file because you don't have the ability to talk to the file system, that sort of thing. So that's one of the advantages of having this sort of flexibility plus namespaces is you can control what language features are visible at any point in time. Racket uses this a lot. Racket is really built as a tower of languages on top of each other. But that's also just like an old Scheme technique as well. Okay, so that's very cool. So thank you for that. And another pointer was to the Hopple. I think this is History of Programming Languages 2, the Hopple 2 paper on the evolution of Lisp by Guy Steele and Dick Gabriel. Of course, Guy Steele was co-creator of Scheme with Jerry Sussman. Richard Gabriel is a famous Lisp hacker and AI researcher, worked with John McCarthy, and also is famously a poet. Anyway, this document, let me see if I can open up I think I've got the PDF here so I could search it better. Hold on. PDF, here we go. So I was looking for quasiquote and having trouble finding things, but it's because they call it backquote. Yeah, common Lisp backquote, right? So this is one of the annoying things, like trying to look for something. Okay, so here you have the comma at, that's the unquote splicing, right? And here it's talking about common Lisp backquote syntax is derived from this. So there was a language called MDL I was talking about. So you get to hear the history of where did quasiquote come from, and then you have Lisp machine Lisp, and then we have some more quotation and backquote facilities, and Mac Lisp and Scheme and algo-like parsing and all that. So so I think this is a very nice document. I think it's interesting anyway, if you're interested in like the history of Lisp and the design of Lisp, to look at this. And, like I've said, I think that the history of programming language books, especially the early, probably the first two, are extremely interesting. Now, I haven't read the latest Hopple proceedings, and it'd be interesting to look at that. And that's more contemporary, and I think that is definitely useful to try to understand like the languages that are currently in use and currently popular. Where the design of those came from, what were the design decisions. So I definitely recommend reading about those as well. I like reading about the things that were old enough that I never used those languages. Those languages were not in use when I was learning to program, like Jovial. Like I never had a chance to learn Jovial. I mean, you're doing some serious retro computing now if you're using Jovial, probably. So I like reading about the old things, because you have people who the people back then were just as smart as people today, and often they were coming from different backgrounds. You have a lot more people coming from math or physics or electrical engineering, and they had big ideas, and they were also doing things like trying to create artificial intelligence, things like that, or machine translation between natural languages, and they were doing it in very constrained environments computationally, and they were using very different techniques often than what's being used today. So I just think it's very interesting to look at. look at the problems they're trying to solve. Why were these languages designed? What problems were the languages trying to solve? What were the design decisions? What decisions did the community or the designers later decide were probably a mistake? Which features actually made sense? What were the combination of features that were powerful? All that. Very, very useful. So anyway, I think if you're interested in learning more about quasi-quotation and quotation and in the history of Lisp, great paper. Hopple 2 paper, I believe. So that's great. And then, more generally, I just want to go back and reiterate this idea that so far for Scheme, I mean, this is episode 13. I've already gone, I don't know, most of these episodes are 2 or 3 hours. So we've already gone I don't know, 25, 30 hours in. And we're basically at cons pairs. We can cons things. We can, quote a symbol. We've learned, quote and quasi-quote and unquote splicing, cons. And then we have things like car and coulter to traverse the pair structures, and null question mark. And we can quote the empty list, and, we can quote an entire list or tree structure. We know about the dots. We know about the dot and pointer notations, but still, all of this comes down to, sort of S expressions and cons pairs and understanding these structures and how to build them in different ways. So this is what I mean, when I've talked about programming in an elementary way. It doesn't mean simple. Elementary doesn't mean simple. It doesn't mean easy. Just means that there are few parts, and generally those parts, the other part of it is, the other aspect of it is that these parts compose. Okay, that's very important to me, the composition. So we spent a lot of time looking just at these pairs. Okay, that also kind of reminds me of Vibe, and his beta GM is like, okay, how long are we going to spend, talking about spreading creep? Well, all the time, right? Because spreading creep is like a superpower of Zerg, and you always want to be able to spread creep. But in addition to just making sure we really understand how these things work and what a proper list is and what it means when we say a dot in a structure that's printed out, I also just want to draw attention to the fact that even with this tiny little language that we've been looking at, first of all, there's sort of this mini game aspect that Day 9 would talk about, cons, quote, quasi-quote, just with that, we already have kind of a mini game. So especially as soon as you have quasi-quote and unquote splicing, that's plus quote, that's like a whole mini game. You can do all sorts of bizarro things, like in Alan Baldwin paper, for example, shows a bunch of those idioms. That's a whole little mini game. But not only is there a mini game and getting good at quasi-quote, getting comfortable with it and comfortable at reading these things and knowing what happened when you evaluate that expression, what the printed answer will be and where the dots will be, if any. Not only is there that mini game aspect and being good at it, but there's also a design space aspect, which is, cons doesn't have to behave the way it does in Scheme. It doesn't at all. And in fact, there's one alternative is from this paper, Cons Should Not Evaluate Arguments, a very famous paper from Daniel P. Friedman, who was my advisor at Indiana, and David Wise. And it's 1976, and it's an IU Tech Report, Tech Report 44. Okay. And it was printed, okay, there's a famous name, Robin Milner, in Automata Languages and Programming, Edinburgh University Press, 1976. Now, unfortunately, the tech report doesn't seem to be available online. I looked for it and I couldn't find it anywhere. That really annoys me because this is like a really famous paper in the history of programming languages. So, you could make the argument that, Haskell came out of this paper. Now, if you talk to Dan, he'll say that, this idea of like lazy evaluation has been, had been seen in other guises. But part of the idea is that, if you write the paper that people can refer to and read and understand and point other people to, then something that was maybe folklore or maybe seen as an aside or maybe mentioned in some other paper or report or documentation for some system, now it's like much more explicit, right? Like, here's the idea: Kant should not evaluate his arguments. It's right in the title. And this allows you to have non-strict operations, like, you can get lazy evaluation type thing. So, you get streams and all that. We'll look into this, play around with this. But the idea is that Kant doesn't have to behave the way it does in the scheme, right? This is an important idea, and it's an old idea. This is almost 50 years old. And the idea had appeared in the community in some form before this, so it's at least 50 years old. So my point is, even with something super elementary that we're playing around with, it doesn't have to behave that way. It could behave a very different way. And if you want to get something like Haskell, it needs to behave a different way. So that's one way cons can behave differently. And then, here's another paper. There are two papers by Henry Baker. And I love the title of this one: Kant should not Kansas arguments. What a great title. Henry Baker has all sorts of great papers. Or a lazy alloc is a smart alloc. Lazy allocation. Okay, so that's an interesting idea. Okay, and then there's a follow-up paper: Kant should not Kansas arguments, part 2, Cheney on the MTA. All right, so here's a little joke about a song from the Kingston Trio, Charlie on MTA, that this is like the Boston MTA, that he'll never return, and this is like tail recursive calls never return, that sort of idea. So nice little Massachusetts related, Boston related pun. So you could see that in theory, you could have a whole series of papers, just like the Lambda, the ultimate X papers, right? Like the Steele and Sussman papers about scheme. You could have a whole series of papers: Kant should not X its arguments, for some X, right? So that could be a whole series of papers. So okay, what else should Kant not do to its arguments? Or what should it do to its arguments, right? So we already said it shouldn't evaluate its arguments, and maybe it shouldn't even Kant its arguments. Well, what does Kant do? And so that's an interesting question now. It's like, well, how else could Kant behave? And okay, so here's another variant of something like cons, is something called frons. And instead of having lists, you get what are called ferns. So Guy Steele gave a keynote for Dan Friedman's 60th birthday Festschrift at Indiana. And he gave a talk called Dan Friedman Cool Ideas, which is on my YouTube channel. I'm very happy to host the talks from that Festschrift. This is a great talk. I highly recommend it. And if you're interested in Lisp and Scheme, here's Guy Steele, co-designer of Scheme, and also he co-wrote that Hoppel paper on the history of Lisp. And he also, famously, wrote this book on Common Lisp, the standard. So, and he's also been involved in the design and cleaning up the design of Java, especially its memory model, and also the Fortress language, and all sorts of really interesting things. So I definitely recommend this keynote. And the cool thing about the keynote is he's going through the history of ideas that Dan had, and he's pointing out the ideas that he thinks are worth revisiting. Very close to my heart. And one of the things he points to is another Indiana Tech Report 104, called Fancy Ferns Require Little Care, also with David Wise. And this is 1981. And this was printed in the papers in Symposium on Functional Languages and Computer Architecture. So this symposium, which you may not have heard of, merged with another symposium to become ICFP, the International Conference on Functional Programming. That actually half of it was a symposium on functional languages and computer architecture. So this is an ICFP paper before ICFP existed, actually. Once again, here we go. Even the abstract's not available. Please see the full paper, and the tech report's not available. But I found this interesting, and so for my dissertation work, I worked with Dan, and also we worked with Joe Neer and Ramana Kumar, and we revisited the fern stuff and the frons. And in my dissertation, so here's the GitHub for my dissertation. My original dissertation, like historically, PhD dissertations are double space because, back when people had typewriters and all that, people would like mark up things when editing between the lines. But it makes the dissertations really long and kind of ugly. So I cleaned it up again and made it single space, and I released it under a Creative Commons license, and should typeset under ZLaTeX, and also I've got the PDF here. And so if you open the PDF up in part 5 of my dissertation, at some point I'll probably talk about my dissertation and how I structured it and the parts and all that, because if you really want to get into miniKanren, you should read my dissertation. You should read other people's dissertations. Okay, so dissertations are actually great. Dissertations are actually much easier to read usually than research papers, even though they're longer. And the reason is because they are long, right? It's the reason I'm making a whole bunch of videos instead of trying to squeeze it all into 15 minutes or whatever, right? If I knew how to squeeze everything into 15 minutes, I would do that and be done with it. But I don't. I know how to do it in maybe 100 videos or 500 videos. I don't know. I have no idea how many videos I'll make. And same thing with the dissertation, which is, if you have 198 pages to describe something, that's how long this one is, then, you can talk about background, you can talk about context, you can explain ideas and build up ideas. You can try to write the dissertation to be approachable by someone who doesn't have advanced training in programming languages, that sort of thing. So I tried to make my dissertation as accessible as possible. I took great pains to try to make it readable by people who weren't specialists and who are working programmers and hobbyists and so forth. And I think to some extent I succeeded. I've gotten feedback that for the most part, the dissertation is easy to read. I also got feedback that the nominal logic part was not easy to read, which I believe. I believe, because I think that's just a tricky. I've gained more appreciation for how tricky that topic is. But anyway, part 5 of my dissertation is on ferns. Okay, here we go. Chapter 14, techniques 4. Okay, so here we're talking about bags of techniques, right? The Feynman approach, have a bunch of techniques. Well, here's a technique, which is a fern. Okay, in this chapter, we provide a bottom-avoiding generalization of core miniKanren using ferns. Okay, so you can actually build a miniKanren on this data structure. A shareable data structure designed to avoid divergence. So this is kind of, we have this operator called frons, and frons is kind of like cons, but the idea is that it's designed so that if you're like consing up expressions whose evaluation can diverge or loop forever, the system can still work. And yet, so you can build these lists that are basically lists of computations. And when a computation completes and produces a value, then it sort of gets promoted towards the front of the list. So you could use this for like multiprocessing and things like that. So it's like an operating system level construct in some sense, or a concurrent programming construct, or maybe a parallel programming construct even. And so, we have variants. So, So we have cons, but we also have this other thing, cons, this is pronounced bottom. And then now we use, instead of car, we use car bottom and cutter bottom. And a note here about the typesetting. So here, that italics, that means that this cons is just like, that's a variable bound to a function, whereas this cons, that's syntax. This is like a macro. And then car bottom and cutter bottom, those are just like functions or procedures. So, this is something worth looking at. Okay, so in fact, I will put this in our ladder practice. Okay, I'll put this on the macro side. Let's. Oops. Oh, come on. There we go. Please read chapter 14 of my dissertation on frons and ferns. Okay. And my dissertation is, thesis.pdf. Okay, here we go. Think about the difference between between schemes, regular cons and pairs and lists, and frons and ferns. At the level of language design and problem spaces and trade-offs. I'm not going to ask you to understand like the implementation differences, okay? But take a look at those, and I'm curious to see how much of it you can understand. I think you can understand the basic parts of the ferns and the frons stuff, having seen cons already. Just be aware that when I'm talking about divergence, I'm talking about divergence equals infinite loop. Okay, we can write an expression that just runs forever, never produces a value. So. And we have the notion of a computation, right? It's like we have some expression that we're evaluating and it's producing a value, maybe it runs forever. Okay, so it's a different sort of beast than we're normally dealing with cons. But the point is, cons can be riffed on. Okay, so cons, we can have a cons that doesn't evaluate its arguments. We have a cons that doesn't cons its argument. We can have this notion of frons or the cons, bottom is the way it was written. Those are a few variations. I'll mention a couple other variations that we can have with like pairs. Is there's also something called hash consing. So here's a Wikipedia page on it. It's a technique used to share values that are structurally equal. When a value is constructed, such as a cons cell, the technique checks to see if such a value has been constructed before, and if so, reuses the previous value, avoiding a new memory allocation. So in Scheme, every time we call cons, we're actually allocating memory. We're actually creating memory, a new space in the heap to hold the cons pair. And with hash consing, if you're consing up a structure that turns out to already exist in memory, at least some of the time with your hash cons, you can tell that. And instead of producing, a new structure, with the hash cons, you just get back the old shared structure. So it avoids allocation. And also it means you can check equality of things in constant time. if they're hash cons equal, if you get back the same structure, like you can check to see if they're the same thing. So if you cons up two really complicated large structures, like nested tree structures, using hash cons, if hash cons has produced the exact same structure for both, with sharing, you can tell that in constant time. You don't have to traverse the tree structure to tell if they're the same or not. So that's a different notion of how cons can work. Okay. And then, so that's stuff with cons, variance and cons, and then there's also, quotation. Okay. So quote can work in different ways. And so there's this 3-Lisp language from Brian Cantwell Smith. It's very famous. Procedural reflection in programming languages, although the claim here is that reflection in that document is more like what we would call reification, which is like making something abstract, concrete, or real. And so there's you have this tower of interpreters and this reflective lambda. And there's also like a different notion of quotation, is my understanding. That quote behaves differently. So a very interesting paper full of interesting ideas, but a different behavior of quote. Very cool. Yeah. So here you can find the document. So here is code implementing this in Common Lisp. Someone create a repo, and then here's like the original document. So if you want to dig into that, this is pretty advanced stuff, but my view is, in addition to learning this elementary style of programming, we also want to be exposed to ideas, and this is something we're just going to have to keep working up to, right? It's like the spreading the creep. We'll get faster and faster at it. We'll get better at it. Okay. Trying to expose you to ideas that are considered important in Lisp programming from a programming languages, applications, research, history of the languages type standpoint. Okay. So, if you look at a document like this, it may very well be the case that you're not able to just open up in the middle and follow what's going on or read the code, especially if it's Lisp code from 1982. I would probably have trouble reading this code, especially given all the meta interpreter stuff. This is not like light programming. This is actually really, really hardcore thinking about the foundations of reflection and reification and all that. So this is a very deep paper or dissertation, but you could try to do things like read the introduction, see if you can understand the problems trying to be addressed, those sorts of things. You can also do things like look at the list of citations in the back, look at the bibliography. That often gives you a lot of information. Look at the conclusion, So if I have trouble reading something, I'll skip around. It's like, okay, I'm stuck. Let me try reading the conclusion. And sometimes I'll do things like start reading the paper backwards because maybe there's something critical at the end of the paper that I just missed. Or maybe I'll just skim the whole paper, try to understand the sections and look at the code and look at the examples and the figures and read the captions, and then go back and try reading it again. I may have to try reading the paper many times to finally get through it. And, with a document like this, you could read it many times, I'm sure, and each time get something more out of it. My claim is you shouldn't be afraid of this. Just be aware that, it's sort of like diving into the Shea scheme source code. There are going to be things you don't understand, almost certainly, unless you're a super expert, scheme hacker. And even then, you probably are not going to know some of the things in Shea scheme because it's got its own unique way of doing things, this unique setup. So can you read this documentation straight through at this point? Probably not. But you could look at it and start trying to get an idea. And then, part of this is I'm just showing you a bunch of things that you should know about that you can come back to later. and poke around, right? So yeah, take a look at it if you want, and try to get a sense of what this is about. And now we have this GitHub repo, talks about it a little bit, right? Here's an explanation of what's going on. There's some code that's running, so you can run this stuff in Common Lisp and play around with it. Yeah, great. Okay, so that's what I want to talk about in terms of this idea that, yeah, we have this really elementary language that we've been learning so far, just like consing and quotes and quasiquotes, that sort of thing. That's really what we've been focusing on. But there's a tremendous amount of richness just here. It reminds me of a quote I heard from David Lynch, where he said that, when he was very young, he probably spent all of his time within 2 blocks, but he said there were entire worlds within those 2 blocks. So that's kind of, their entire worlds within cons and quote and quasi-quote, right? It's like this stuff is much, much deeper than it might appear on first glance. And I'm sure there's way more to be discovered here. Just like with the lambda calculus, schemes, extended call by value lambda calculus, lambda calculus is only 3 types of expressions, which we'll see. And people still study it to this day and do research on lambda calculus. There's some other types of things, related to like cons. So there are immutable pairs. So historically, scheme pairs and in many Lisps, the pairs you get from cons, you're allowed, once you get the cons pair, once that's created, you're allowed to change what's in the car and change what's in the cdr. In scheme, there's something called set hyphen car bang, and set hyphen cdr bang allows you to mutate or modify where the car and the cdr like what contain. A more modern approach or more modern view is that has a lot of disadvantages. So like Clojure is a language that's a Lisp that famously commits to immutability. I think Racket pairs by default are immutable. I don't know what's going on with R7 there, and I don't remember the exact details for R6. But I think like Racket has both immutable and mutable pairs, and immutable by default. In any case, if you want to do purely functional programming, you might not want to have mutable pairs. You might want to make sure that everything's shareable, and if you have a list of length 5, some other part of the program running and isn't going to like just set cdr bang something, and now you don't even have a proper list anymore, right? So if you worry about things like thread safety and all those sorts of things, having immutable data structures is very nice. So that's another variation on cons. Like, are your pairs mutable or are they immutable? There are also ways to create infinite structures using pairs where a pair refers to itself either directly or indirectly. So it has like a loop in the structure, and we'll look at this also. And in the Prolog world or logic programming world, you have this notion of infinite rational terms where, you can, if you were to fully follow everything, fully follow the cars and the cdr pointers and like the box and pointer notations and sort of reify or print out everything, you would end up with an infinite tree structure, perhaps. But there's a finite representation in terms of the sharing and the self pointers and stuff like that. So Prolog 2 famously supports infinite rational terms and unification over infinite rational terms, whereas sort of Prolog 1 and miniKanren, those aren't allowed. All the terms have to be finite. And we'll get into that when we get into logic programming, but that's another thing. You can have pairs that point back to themselves in different ways. And then there are different types of lists. Like for algorithms and data structures, there's something called a skip list, where you can have lists that instead of like having a cons pair, you can have a list that's more like a struct that has like multiple pointers, and the structs can be of different sizes and have fewer or more pointers, and they can point. Some of the pointers like point deeper into the list, so it allows you to skip over. Like when you're cootering down a list, it'd be like if you had multiple cooters. Some cooters go, one pair to the next pair, like just following the box and the box and pointer diagrams like we've been doing. But you might have like longer pointers, like a pointer that's pointing 10, to the 10th, pointer from the first cons pair to the 10th cons pair that you can follow directly. And, that's sort of idea. Now, with standard cons pairs and scheme, that's not supported, but you could imagine, implementing or maybe override cons and scheme, and, maybe you make skip lists the default. Okay. Maybe you use structs or records, in Racket or scheme to have a version of cons that's based on skip lists by default. And that allows you to have faster asymptotic efficiency when you want to get to some element in a list. Like, you can, it's not as fast as an array, it's not random access, but allows you to get to elements more quickly. So you could imagine versions like that, right? What if your cons was actually consing up skip lists? I don't know. And also you can get into types. You could say, if you're in a language like ML, you might say, well, you're only allowed to have proper lists. Okay. You're not allowed to have improper lists. You can't have anything that would be the scheme equivalent of having a dot. Okay. So you have types, layer type system, like Henley Milner or something like that. And just in general, these different notions of cons, different notions of quotation, they remind me of the different notions of variable that pop up. So for example, when I first learned to program in BASIC, I thought I knew what a variable was, and then you would change the value of the variable. Like, it's x equals 5, and then later in a loop, maybe you say x equals x plus 1 or whatever, all that sort of thing. And then in functional programming, a variable might not vary. You might have variables that are not allowed to vary. Okay, so it's more, and in recursion, you might have variables that shadow each other. They have the same name, but they actually refer to different values. And in logic programming, you can start talking about variables that, whose value you don't know, that you're doing this unification operation on, which is like a two-way pattern matching, which we'll get into. Okay, so now you're starting to operate on something you're calling a variable, a logic variable or unification variable, but where you don't actually know what the value of the variable is. But that's okay, you can still use it. And then with like symbolic execution, you have a different notion of a variable. Okay, so there are lots and lots of different notions of variable. And we call those all variables, but they actually have totally different behavior. And in fact, in logic programming, a logic variable isn't even a variable in the sense of a scheme variable. It's really like a value or a term. It's not actually a variable, like a variable reference in scheme. So they're actually, we give the same name to many different things, this name variable, to many different things in programming and programming languages that have very different behavior. We call them all variables. Yeah, and it reminds me of, there's this saying that to the beginner, there are many choices, but to the expert, there are few. I mean, I guess this might be talking about like chess or something, right? Beginner just like, I don't know, I can move any of the pieces. And the expert's like, no, you can only move one. But then there's also this idea of beginner mind, like in Zen Buddhism, which is, okay, let's try to recapture that. Like Picasso talking about, no matter how great he was as a representational artist by the time he was 17, what he really wanted to do is learn how to paint like a child again. And that was, he wanted to see the world like a child. And it reminds me of the Don Cheadle, the actor Don Cheadle story, where it's like, so the stages in an actor's career are, who's Don Cheadle? Get me Don Cheadle. get me someone like Don Cheadle. Who's Don Cheadle, right? It's going to feel like, when you start programming, you're like, what's a variable? You're programming in like C or something. What's a variable? And it's like, oh, okay. Okay, I'll use a variable. And at some point, you're like, I'll use something like a variable. You may do symbolic execution or something. And at some point, you're like, okay, what's a variable again? I know a whole bunch of things are called variable. At this point, I'm not sure. Now that's getting into the research context and the design context. Okay, what other notions of variable are there that we haven't come up with, or maybe people have come up with, then maybe they don't call it a variable, that might be useful? Like which other notions of variable-like objects might we use in programming? Okay. Now, like vibes, worrying about feeling like a broken record. I've mentioned this, that I feel a little like a broken record in that I've talked like kind of big picture a lot of the times, talked about what it means to look at things from a research standpoint or a design or comparative standpoint, talked about how important it is to read papers and to write down your ideas in like a research notebook of some form, or you could call it a design notebook if you want. Maybe you want to focus more on design. All those sorts of things I think are very important. Constantly going out and reading, constantly, exploring ideas and thinking, playing what if, like what if I made this, what if this behaved differently? Trying to understand how design choices in a language fit together or don't fit together. It's very important, I think. Okay, so that's why I've focused on this so much so far. At the same time, I think I've made that point. Okay, so I want you to keep doing those things, keep reading, and I'll keep pointing, I'll still give you macro practice, and I'll keep pointing things out. But I want to start moving more into expanding our elementary language, okay? And in particular, I want to get to the point where we can start looking at artifacts like, we talked about this Lisp 1.5 manual. The bottom of page 13 is a super famous program, the most famous Lisp program ever. Let's see where it is. Here it is. Okay. This is eval and, or eval quote in this 1961 document. So we have eval and apply basically. And so this is a scheme, or sorry, a Lisp in Lisp interpreter, a Lisp interpreter written in Lisp, sometimes called a metacircular interpreter. This is like a fundamental object that we're going to study and manipulate and use. And it's fundamental for many reasons. One, this is what Alan Kay has referred to Maxwell's equations of software. Well, we can manipulate this lots of different ways. We can extend the language. We can play with the implementation. We'll see all sorts of ways we can riff on it. I mean, if you think about it, I was just talking about all the different ways you can think about cons, right? And variants of cons. Well, imagine when we have a whole interpreter for a Turing complete language, right? If we do all that with cons, like we could play a lot of games of this one with this interpreter, and certainly we can. You could spend a whole career playing with this. A couple important points here with this artifact is that one is when we implement this, we're going to implement in Scheme. So it's going to look somewhat different. But if you go back and you look at this and squint, you'll see that it's similar in a lot of ways. And you can see like car and coder and cons, right? And lambda. There's some weird things like label, but you can see quote. There's quote here, yeah. And there's con, which we'll talk about. That's like the McCarthy's conditional operator. So you'll get to the point where you'll be able to read this, okay? But we're going to do it in Scheme. We're going to do Scheme and Scheme. And by implementing Scheme and Scheme, we will make sure we completely understand the evaluation rules of Scheme, how things happen in Scheme. Okay, not in a super optimized way, but in a way that's semantically correct. And and we'll understand that. And we'll have a restricted version of scheme, and we'll restrict it in different ways, and we'll relax the restrictions in different ways. But that will give us a much better understanding of how scheme really works, and what the evaluation rules are, like sort of what the operational semantics are. And then also when we get into logic programming, constraint logic programming, relational programming, and miniKanren, this is going to be an artifact that we care about. So we are going to implement the scheme interpreter in miniKanren, okay, as a mathematical relation instead of a mathematical function. And we are, also going to play games like, so we can implement scheme in scheme, that's metacircular. We can implement scheme in miniKanren. We can implement miniKanren in scheme, that's actually how it's done. And we can implement, things like miniKanren, metaKanren. And then you could do like scheme and miniKanren and scheme and scheme and miniKanren and miniKanren and scheme and scheme and scheme and miniKanren. Okay. That's like getting into three Lisp type things. And then, how do you make that efficient? Can you make it efficient? That's an ongoing area of research with my collaborators. So this is something that I want to get to. It's very, very important. And they're also, just as a pragmatic thing, this is something that's really actually useful to know as a programmer, because there are lots and lots of times where little interpreters come up. We could also look at the compiler stuff. We might want to, at some point, investigate compiling scheme, like in the essentials of compilation, all that. So this is where we're trying to get. Okay, so something like this, but it's all going to be in scheme. And some of this you could see we already know. We already know what car is. We know what cutter is. We know what cons is. We've talked about lambda a little bit. We're going to talk about it more. And we know what quote is now, right? So we could already see that we have quite a bit of this. And you can see, this is actually using cons and catter. Remember, we've talked about catter. That's the car of the cutter, right? So the cat editor, a lot of this we've already seen, okay? So even though the notation looks maybe different, we're already learning a lot of those things. But that's something I want to do. Okay, so we're going to start focusing on things we need to know to get there. So we're going to have to know recursion. We have to know how to write recursive functions or recursive procedures. And in order to do that, we're going to have conditionals and lambda / procedures. I should be careful when I say in order to do that, we have to have conditionals. Okay, so it turns out you can do everything with lambda calculus, which we'll get into at some point. All right. It'd be awkward to do everything with lambda calculus, but in theory it is possible. But we're not going to do that. Okay, we're going to do something extended lambda calculus, extended call by value lambda calculus. So we'll get into all those things. We'll look at lambda calculus. But so we need lambdas and procedures and conditionals and booleans. We've looked at booleans a little bit, but we're going to do that more. And so for conditionals, we're going to look at like if and cond. Okay, there we go. Booleans and truth. We've mentioned this before, but we'll get into that. And then, we're just going to be, we're going to have like type predicates, which we've seen some of. The things like pair question mark, null question mark, list question mark, okay, number question mark, stuff like that. So these are like built-in procedures. They're in what's called the initial environment. We're gonna have to know about environments. Environments. And variable binding. And shadowing. Some of this we've talked about a little bit in passing, but we need to know more. And we have a few other miscellaneous built-ins. plus times, that sort of thing, maybe. 0 question mark. Right? It's not a type predicate, but it's a value predicate. These sorts of things. And we're also going to have to learn pattern matching, which goes along with our quasi-quotation really well. Pattern matching is super useful. And we're also going to have to know our evaluation rules for scheme. Okay. I'm putting that one last, not because it comes last, but that's something we just really have to understand. Now we'll understand it better when we implement the interpreter. But at this point, we'll be able to scheme evaluator. I'll call it an evaluator. This will lead us to being able to write a scheme evaluator written in Scheme. And then we're going to play some games. We're going to have, we have some program transformations. We're going to have things like defunctionalization. And higher order representations. We'll talk about things like closures. We'll have all sorts of interesting things here. And at this point we'll be able to start having fun. There's a whole lot we can do once we start getting into this part. This was really the C311 B521 Indiana University PL courses. So C311 is the undergraduate intro to programming languages course, and B521 is the graduate intro to programming language courses. So I took B521 my first semester of grad school at Indiana, and I was teaching, what do they call it? An AI, an associate instructor for both C311 and B521 many times. I think like 11 semesters between the two. So I know this stuff quite well. So Dan Friedman, basically taught me all this stuff, right? Yeah. So thanks, Dan. So that's where we're headed. And then after that, we can get into like logic programming. Okay. And then along the way, we can fill in and explore, we can do things like macros and hygiene. What does that mean? Why do you need hygiene? Why do you need hygienic macros and lambda calculus and all these sorts of things? Okay. Okay. So we have plenty to do. We have plenty to do. We don't have that much more to learn, actually, in terms of the language. We have lambda, which we've already seen. We've already seen Boolean truth values. We'll see that some more. If conditional expressions, I think we've seen at least once. We'll dive into that a little more and learn cond. You can see cond, by the way, McCarthy's conditional operator. That's also right there. There's cond. Okay, so this is like a conditional operator. That's like, yeah. So we'll learn all that stuff, and the type predicates we've already encountered. Type predicates. We've already encountered things like plus and times and zero, but we'll just go over these again and make sure we understand the evaluation rules. And then we're going to spend some time writing recursive procedures and understanding that, and just being comfortable with that. Okay. And then we'll get in environments and variable binding and shadowing. We've talked a little bit about some of this, but not into the depth that we need to. And then I'll show you pattern matching, and that's really cool. Super helpful, and it goes so well with quasiquote and S expressions. And then we'll make sure we understand evaluation rules of scheme, and then we'll be ready to do our evaluator. Okay, and then we can riff on that all sorts of different ways. With these things that we're trying to understand, the sort of our elementary style programming, I'll reiterate. I mean, I saw this today on one of the StarCraft videos. I forget which one it was. I think it was one of Vive's video. I couldn't find the comment, but someone had the comment, practice is something like practice, train, not so that you can get it right, but so that you never get it wrong. Okay, that's what I mean. Like when I say you're able to do it that level. Okay, you should be able to do consings and using quasi-quotation and quotation and unquote splicing and using lambda and understanding what lambda does and how lambda works and if and cond and all these things. Writing recursive procedures, you want to get to the point where you're just like not making mistakes. Like, yeah, sure, maybe once in a while you make a typo while typing, but you probably catch it immediately, or you immediately catch it when you try running things. And we'll follow Aziz Ghulam's rule, which is, if we try something and it doesn't work and we can't immediately see what's wrong with it, we'll throw it away and restart again. Okay, we're not going to fumble around. That means that we weren't careful enough. Okay, so this is something I think it can take people to get. Well, once again, this is something that maybe many people have trouble being comfortable with. It's like you've implemented something and it's not working and you want to debug it. Sure, look and see if it's some immediately obvious problem. But if you can't debug it like quickly, then you've done something wrong. Like you've written it in such a way that you can't debug it. There's some fundamental mistake. You can save that file to compare with later. That's a useful thing. But redo it from scratch and do it more carefully. And then if that version works, then go back and compare to see, so you can learn the mistake you made and try to not make that mistake in the future. But that's the approach we're going to take. We're not going to tolerate ourselves writing sloppy code. We want our code to be correct. That's why we want to be able to do this stuff with very, very high accuracy. It's okay if we go slow in the beginning. We'll speed up over time. But it's not okay that we're making a bunch of mistakes that are sloppy. That's not okay. All right. So anyway, that's what we're going to start doing. And yeah. I think gone enough. Next time will be conditionals. Okay, let me put that next time. Next time we'll get into conditionals and truth values and all that. Okay, and we'll go from there. We'll just start working on these things and see where we get. But like I said, my standards are very high for understanding and being able to use these things. Okay. Like you have to be able to use them at a point where you need to understand what's going on. This is not Stack Overflow, flail around looking at a Stack Overflow answer. You really need to understand it. Okay. Previous ladder practice, you had some micro and macro. We have some macro this time, which is looking at my dissertation. And, for the micro, just keep doing it, okay? Make sure to practice all those things. And we're going to start coding next time, and we're going to start cutting down on the meta level, big picture, grand conspiracy type thing, and start getting into, the details of how Scheme works and how you implement these features. Okay. So, but keep reading, keep looking for papers, keep looking at Hopple stuff. Okay. And I mean, that's the other macro stuff, which is, look at history of Lisp paper, especially in relation, relational, it's just habit, to backquote and quote. Okay. That's some more macro practice for you. Okay. Alrighty. Well, have a good one, and I hope to talk to you soon. And we'll get into more Scheme, and we'll start getting towards being able to do our environments and relational interpreter, Scheme interpreter, Scheme evaluator, Scheme and Scheme. And then once we've played around with that, then we'll be ready to start looking at miniKanren some. Okay. All right. Have a good one. Talk to you soon. Bye-bye.